The next type is a synchrocyclotron, or in Vladimir Vexler's terminology, a phasotron. This is an accelerator with a constant magnetic field, while its orbit radius increases. To maintain the synchronism, the RF field frequency is decreased during acceleration. One of the first accelerators of this type was built under the leadership of Mikhail Masharikov in Dubna as part of the Soviet military project on creating nuclear weapons. It started operating in December 1949 and has remained a functioning facility to this day. After it completed its scientific program in the context of the military project, it was used for research in meson physics, including, for example, very interesting research from the viewpoint of muon catalysis of thermonuclear reactions and moving toward cold thermonuclear reactions. From 1969 on, at the initiative of Masharikov's deputy, Venedikt JILEPov, after whom the laboratory is currently named, the first experiments began on the phasotron in using accelerated proton beams and pi mesons for cancer therapy. During the many years working in this field, specialists from the Laboratory for Nuclear Problems have gained vast experience in forming dose fields on an object exposed to radiation by means of beam diagnostic methods. In addition, a wealth of expertise has been built up by the medical personnel working in this area. Currently, the phasotron produces around 100 radiation therapy treatments per year. Unfortunately, its beam is expensive, and it cannot be used as a basis for a clinical facility. We expect it to be replaced with a modern, cost-effective superconducting cyclotron. Experiments and treatment of patients will be carried out based on more advanced technology. The next type of RF resonant accelerators, which is referred to collectively as the synchrotron, has two subtypes: an ion synchrotron and an electron synchrotron. There are no electron synchrotrons in Dubna. These are synchrotrons that operate with a constant accelerating field frequency. However, in Dubna, the first proton synchrotron had functioned for many years during the Soviet Union, and it still holds the record for the weight of its magnet yoke, amounting to 36,000 tons. The idea of a synchrotron had been introduced by Marcus Oliphant in the UK in 1943, before the proposal was submitted by Vladimir Vexler. Oliphant proposed to vary a magnetic field in such a way that the curvature radius of the particle orbit remained constant, and the RF field frequency was determined based on the particle revolution frequency. Theoretical underpinnings of this type of accelerator was put forward by Vladimir Vexler when he formulated the phase stability principle. The first tests were run in the UK as part of the implementation of the UK's nuclear project. In 1946, the 4 megaelectron-volt betatron was converted into an 8 megaelectron synchrotron that accelerated electrons. Today, the world's first superconducting heavy ion synchrotron is operational at the Vexler and Bolden Laboratory of High Energy Physics, the nucleotron. The perimeter of this accelerator is about 250 meters. It accelerates heavy ions to the energy of 4.4 gigaelectron volts per nucleon and light ions up to about 6 gigaelectron volts per nucleon. It accelerates protons almost up to the same energy level as the synchrophasotron, which is a little less than 12 gigaelectron volts. It is being utilized for experiments in relativistic nuclear physics and spin physics. The nucleotron beams are used and are planned to be used for conducting research on applications of high-energy, heavy ion beams. Within the framework of the New Accelerator Collider Complex, NICA, which is currently being established, 3 accelerating facilities of the synchrotron class will be operating at JINR. First, it is the booster synchrotron, which is an element of the heavy ion injection chain for the nucleotron. Second is the existing nucleotron accelerator, and the 2 collider rings in which an experiment on initially heavy ion colliding beams and then on polarized beams will be implemented. Besides this, the NICA complex includes 2 linear accelerators, a light ion linear accelerator and a heavy ion linear accelerator. As a short summary of my lecture, I could tell you that practically all existing accelerator types which have been classified by mankind could be found at the Joint Institute for Nuclear Research. If you'd like to find out how a certain accelerator type works, how it was designed, and how it operates, visit us in Dubna.